Hello and welcome to this IDM Technologies recorded webcast. We hope you will find this webcast both interesting and valuable. If after viewing this recording you are interested in more, please go to our IDM TM webcast YouTube channel for more recordings or sign up for one of the upcoming live sessions at www.idm.com/find/web_seminars. Now let's go over to the presenter.
Welcome everybody and thank you for joining us for the webcast titled MQA, the golden standard for device model validation. My name is Vincent Launois and I'll be your host during the session. Today we will hear a presentation by Cedric Pujol and Janice Deng. Cedric is the European application engineer for device modeling design software within Agilent ESOF IDE organization. He is now leading the RFIC pre-sales activity in Europe, as well as device modeling solution. Janice Deng is a worldwide application engineer supporting the product MVP and MQA. She is based inside the Agilent ESOF IDE division, working closely with the software developers. For everyone's comfort, this is a lecture-style meeting. However, this webcast is designed to be interactive between you and our presenters. So you can send questions in writing at any time during the session through the Q&A functionality of the WebEx meeting. Please address your question to the whole panelist so our experts can read them directly. Our presenters will make every effort to answer your question during this session, so I do apologize in advance if we don't get to yours. But don't worry, if we run out of time, our presenters will respond to the remaining questions via email. While the answer to your question may be published for others to see, we'll keep your identity private. Please be reminded that the webcast will be recorded, so you can review and share with your colleagues at any time. Now, let's move on to the presentation. Welcome everyone. Cedric, you now have the floor.
Thanks Vincent. Hello everyone, I'm Cedric Pujol. So as Vincent told you, I'm applications engineer in Agilent Technologies. And I'm also the device modeling solutions lead for the EMEA region. I'm glad to welcome you on this webcast, which will deal with introducing our recent extensions to the Agilent ESOF device modeling portfolio. So for about 20 years, ESOF has been deeply involved in modeling, linking EDA tools with measurements and model extraction, thanks to the well-known software called ICCAP you surely have heard of. We have been working with the major foundries worldwide on various substrates, including silicon, gallium arsenide, gallium nitride, and also bipolar and SOI technologies, to characterize physical devices and create models that ended up in process design kits, also known as PDKs, on the most renowned frameworks, including Cadence, Mentor, Synopsys, and of course, Agilent IDS. Last year, Agilent acquired a company named Axelicon to broaden its device modeling offer, extending to model qualification and also device modeling consulting services to help foundries and also design houses to provide and develop device modeling. So this extension to the model qualification has been really beneficial to answer some common questions that a lot of design houses we have worked with had about PDK and also EDA electrical simulators qualifications. The recent industry changes going from design centers in large foundries as IDMs to fab-less or fab-lite design houses implicitly led to different relationships between the foundries and the design centers. It's not unusual that even small design centers challenge their foundries, including the largest ones, in terms of qualification of models, such as what could be the difference between the modeling and the measurements, and also questioning them about the supported simulators and so on. This needs to go beyond simple data sheets, as established fair discussions between the design houses technology departments, also known as foundry interfaces, and here is a list of the common questions we heard from the design houses we worked with. So we can divide them into three main parts. The first one deals with the technology itself, so by scanning the Foundry portfolio to select the needed options, taking the price into account for the targeted designs. So do we need, for example, to use the low power MOSFETs or the high-speed transistors? Do we need an SOI substrate? What's the real difference in leakage current between the offered options? Or even is it worth going down in electrical nodes? Also, it's pretty difficult to compare two foundries when the design houses have decided to second source. So how do I thoroughly compare the threshold voltage of the MOSFET of a foundry A to a foundry B, being sure I'm really comparing apples to apples? The second block of questions, when the foundry has been selected, is the PDK impact when a new release comes in. We have seen foundries releasing over thousands of PDKs per year. So, but what does it change to your design? Other potential source of interrogation is that the selected foundry has a validity range for its own qualifications in terms of bias or temperature, for example. So what will happen if your constraints are different, if you're designing embedded designs, if you have a different temperature range because of aerospace constraints, or if you need higher power than the power that is qualified for by the foundry? The last series involves more EDA. If foundry A releases its PDK on only one simulator or an older version of your current simulator, what's the risk you're taking to use your preferred version of your golden simulator? And in the case your EDA vendor is introducing a very tempting new release, could you really upgrade without risks? So for answering these questions, Agilent is proposing two tools called MQA and MVP, able to help you establishing this dialogue between the technology department and your foundries. My colleague Janice Deng will go in much further details about this during our presentations and demos. In a nutshell, MQA is aimed at qualifying the models, comparing different foundries, different simulators, different versions of the same simulator, or even if you have them with measurements. MVP is the right tool if you need to retarget some foundry models to your specific applications. The aim of these two tools is really to provide a seamless solution to ensure that the foundry models you're using can be trusted in your specific environment. So I will now let Janice handle the presentations, and I'll be there along with Vincent and Janice at the end of the talks to answer to your questions. Have a nice webcast.
Okay, hello everyone. I'm Janice Deng, application engineer in Agilent Technology. I'm supporting MVP and MQA worldwide. I'm very glad today to give an introduction on MQA, and hopefully you will find out in the end of this webcast that as a golden standard device model validation platform, what is MQA, what MQA can do, and how MQA can benefit or contribute in our daily work. So let's start from an overview of MQA. Here is a complete SPICE modeling flow for the Foundry model modeling engineers. Normally, we do the measurement or device characteristics first for all different device geometries, temperatures, etc. And then we use the measurement data to do the model extraction, to extract the parameter. You can either use IC-cap or use MVP to extract the model parameters. Then the model card or model library extracted will be qualified before delivery. This step of verification and documentation is exactly what MQA can help. With MQA, we can automate the QA process and also improve the completeness of verification coverage. So here, this step is where we use MQA. Then, as a design house, we receive the model library from Foundries. What are the challenges or requirements for us? The model library has been obtained from the Foundry. It should be checked against the two main parts. First one, we can call it generic checks. For this generic checks, we check physical behavior, such as the target scaling behavior in terms of channel length or channel width. We check parameter range. If we are using binning model, we can check bin continuities, etc. Then we can check model behavior in terms of corners or statistical model. The crossover between different corners or the statistical behavior. And then also different test circuit performance. So all these generic points should be already qualified by Foundries, we'll ask. That's true. Foundries did a very complex qualification process before the delivery. However, from a user point of view, we always do the double check of all these generic points, just to avoid of over design or avoid of simple mistakes. And then, according to different design requirements, we may also need to apply some more specific qualifications, more focus on the device geometry we will use in our own design, or the special voltage supply, temperature, or even the special target I want to pay more attention to. That can be very specific on a single simulation point across different devices, instead of the full documentation Foundry provided to us. There are also some special effects, such as if I'm working on analog design, I may be more interested in the GM behavior or high-order derivative result, or even mismatch model. If I work on very advanced process nodes, I may need to be very careful on layout-dependent effects, WPE or stressing or other special effects. So all this are user-specific QA checks. Finally, the check which cause more headache, all kinds of comparison between different simulator formats, simulator versions, different model types, different foundries. With the model complexity growing, the model library turns to be more and more difficult to read or even understand, which of course gives more headaches to apply all different comparisons. So all these checks above means we need to handle a huge amount of data and then quickly find out the issues occurred. Finally, generate the detailed reporting for all the QA results and flag the issues. And this requires a comprehensive, flexible, and a customizable tool to make the whole QA process automation, to use more machine time than our engineers' labor work. That is the first idea why we develop MQA and why MQA has such a lot of customers worldwide. So if we simply summarize MQA, the three letters stands for Model Qualification Assurance Program. It's very straightforward. It's a model qualification assurance tool that can verify model libraries, do all kinds of comparison, and generate a report. MQA can pass model libraries directly with even growing complexity of library structures. And then we qualify all components inside the model library. Secondly, it can compare model libraries between different simulator versions, foundries, or process nodes without rewriting thousands of lines of netlist, and also write different netlists for different simulators. And it's an automated device model verification and documentation tool. that can analyze huge amounts of data on behavior of curve trends, kinks, value range, or crossover, or etc. And then we can generate a detailed report just with a few mouse clicks. So to better understand how MQA works, let's take a look at this architecture graph. We can see MQA in the middle as a platform. We can see several inputs. Firstly, we have device libraries. It can be a single model. It can be a very complex model library. It can be one library or multiple libraries from different Foundries or from different SPICE simulator format. And then besides the model library inputs, we may have measurement data. It can be pure silicon data, or it can be electronic test data, or it's just the target you want to fit. So here is the two inputs. One is library, another is measurement. And then we can see the rule files here. The rule file are used to drive MQA. As we use the rule file to tell MQA how to generate netlist, what to plot, and what to check. Rule file contains a set of information, including the titles, sweep conditions for all the instant parameters, and bias conditions. It may contain graph options. We need to show the graph linear or log scale, or what kind of plots to show. It contains result expectations, what kind of check you want to apply. And then the flagging criteria means to reach what criteria MQA will report error. So all this, we provide a package of rule file based on our knowledge and generic physics behavior for different technology. As a user, you can also develop your own rule file to apply your own QA flow. So with all this input, model libraries, measurement data, and then rule file, MQA will generate netlist automatically and call the simulators according to your model library type. The simulation result finally will be saved to MQA database. This database can be easily shared and viewed in MQA. At last, we can generate a report from MQA result file with some different report format, such as PDF or HTML, Word, or Excel, PowerPoint, etc. So this is the whole architecture of MQA. Generally speaking, MQA is a platform to help users use rule file to drive different applications. We generate netlist, run it automatically, and organize, analyze the result. Thus, we can use MQA as, firstly, a SPICE model qualification tool. It's knowledge-based and rule-driven. It's capable to handle huge amount of data. We can detect all kinds of issues like kinks or like trend error. We can use MQA to detect all these kind of errors. And then we can use MQA as a design interface tool. We do all kinds of comparison, like different corners. We'll overlay with different sites, different Foundries, different test data. And then we can use it as a design documentation and a QA result sharing tool. It's very easy to generate a report automatically. It also can be a communication tool between different groups internally or between different engineers. So before we go into some technical details, let's take a little break from the slides, and I will show you a short live demo of MQA, just to give you the first image that what MQA looks like and how to use it. Here you can see the main GUI of MQA. The MQA tool is based on Java, so the GUI is quite user friendly. Normally we start with a feature we call it Lib Explorer. In this feature, we can add all different model library into MQA. MQA will pass model structure, and then we use this model to create project and run the QA result, run the QA process. So we just simply add a model. For example, it's a H5 model from Foundry A. For example, I load this model library, and MQA will pass the structure. It contains transistors, it contains different diodes. For each channel, we have different corners. It can be a subcircuit, it can be a global compact model. And then I can check one transistor to apply the qualification. For example, I check NCH. MQA will pass the information for this model. Also, here's a constant table that we can change. That means even I change the voltage, I change the process, I don't need to rewrite the rule file, rewrite netlist. I just need to change some constant in MQA setup. And then this model is checked. That means it's already available to create the qualification process. And then I have the second Foundry. It's the same H5 model from Foundry B. It's with same structure, and I can select the corresponding NCH to apply the check function. Then I have now two libraries from two different Foundry. I select the same transistor, and I can create a comparison between these two fab model library. We talk a lot about the rule file, so I choose the rule file I want to check. Here we can see in this rule file I contain different comparisons. If I want to run one of them, I can just simply run this project. When I start to run the MQA project, MQA will automatically generate the netlist and send it to H5 and run it, calculate the target. For example, I run the rule ID set versus L. So MQA will generate netlist and calculate ID set result. When the session completes, I can view the result inside MQA. In MQA, there are mainly two parts. The left part is the tree list. All the projects has been done will show here. So I can see from the list, and when I click on the running result, it will show the simulation result. For example, this rule I've run as ID set versus L. So I have two groups here. The curve stands for fab A, and the dot line stands for fab B. So it's a very easy few clicks. I can compare the difference behavior between different foundries. Then it will calculate the differences between these two ID set behavior. This is the plot, and if I want to just check the real data, I will also have the table, one column with ID set of Foundry A, one column with Foundry B. And then here's the differences between these two foundries. So then we will ask, I have another situation that I have different simulators. It's the same. For example, I have an ADS model. I have an ADS model. It's the same as select the model to check. And then say I have a SPEC3 model. I load these two models, and then I want to compare them. So if I do it manually, I need to write ADS netlist, I write SPEC3 netlist, I run it differently, I collect all the data and compare them. And then in MQA, I just select these two models. I can still use the same rule file and run the same rule, ID set versus L. So this time, MQA will generate different netlists for ADS and SPEC3 and call ADS and SPEC3 in background, collect the result, and calculate the target. When it's finished, we'll see similarly the ID set versus L result. The difference for this time is we will find out it's a perfect match between these two models. That means it's the same model in two different simulators. So if you have noticed that I load all these four models together into the same Libra Explorer feature, you can tell I can load even more model libraries. And when I create the comparison, I can select easily from across different model libraries to select the different models to do the comparison. So we can say that there's not really the limitation in MQA to compare across different versions or different foundries or different simulators. In MQA, it's all in the same level. You can choose freely from different foundry or different simulators. Okay, so let's stop the sharing of the tool and get back to the slides. Now, I hope you have a first impression that how to work in MQA and how easy to do all this model comparison through a few just mouse clicks. Then we go to more details to see what MQA provides and what we can customize based on our MQA platform. Here is some basic facts that MQA supports all different SPICE models. We support transistors like typical BSIM3, BSIM4, some advanced technology we can use HiSIM or PSP or even BSIM IMG or SOI. And we support bipolar, different model type, passive devices. From the version 2012.07, we start to support Angelov GAN, and Angelink HBT model. From the different model types, we can support global model or binning model. Of course, we use subcircuit or macro model, and even if there is Verilog A code involved, we can also do the simulation. Besides a single model, we also support any circuit block validation. User can implement their own circuit design and run the simulation based on selected model. From the different simulator formats, we support most of the popular simulators in the industry, like H-Spice Spectre, ADS Aldo, Spice 3, and from the latest release of MQA, we start to support Golden Gate and FineSim. Besides the commercial simulators, we did several projects to support users' in-house simulators as well. So there's also measurement data. Sometimes we support all the silicon-based data, IVCV, as parameter, noise, or electronic test data format. The format comes from different tools, different measurement tools. And also from the latest release, we start to support ICCAP SQL database. If we simply divided MQA applications to 3 catalogs, first one will be check and analyze. We can do a single model QA to check the trend or the physical behavior parameter ranges. Or we can do the model library QA, like across different corners to check the trend or crossover. And then there's a statistical model. We can do the like histogram plot or to overlay the Monte Carlo simulation together with corners. Also mismatch. If you have measurement data, of course, we can overlay model and the data together. Benchmark circuit. Users' own special test benchmark can be implemented into MQA as well. Then from the small demo I have shown, I think you will you already understand how easy we can compare different model versions from different foundries, different simulator formats, or process node inside MQA. As we can say that there's no limitation between all these different things. In MQA, it's just a model. You can compare it with any other model. Then the last step is report. To generate report in MQA is very easy. We can just with a few single clicks to generate different format reports such as PDF or Word or other Microsoft format. So we mentioned about MQA default rule package. There are several different levels. Firstly, the simulators. Here's all simulators MQA support. And for each simulator, we support different devices. For example, for transistors, H-Spice transistor is divided by different levels. For example, 49 is BSIM 3, 54 is BSIM 4, etc. So for each, from each folder of rule file, we have such a long list of different rules. All these default rules are included in your installation package. That means after you install the MQA, you will find out all these rule files. It contains a set of default rule files, including like parameter range, IV curves, or scaling plots, derivatives, some ET data or intermediate variable checks. For binning model, we have bin continuity, or we have some key model parameter checks. So all these default rule sets can be used directly for your trial version. And then we talk such a lot about rule files. Let's just take a small look inside what looks like the rule file. The rule file in MQA is a purely text file, which defines how MQA performs certain checks on certain objectives under certain conditions. Here's a sample of a rule. It's an ID set versus L rule. You can see as we just run it. So what this rule looks like. So this rule, firstly, we have a title that will show in MQA tree list. We have already seen that. And then we have conditions. Since the criteria may be different from NMOS or PMOS or different conditions. In this case, we have device type equals to 1 stands for this rule will only apply to NMOS. And then we have a section to define all different iterations or sweeps. There's instant parameters iterations, instant parameters loops. For example, channel length, channel width, temperature. Or if you have more than this in instant parameters, you can also define the loops. And then there's bias conditions as well. There's like VGS, VDF, all these bias can be defined in loops section. Following by the instant parameters definition, we have targets. We can define a single target like ID set, or we can define multiple. We can use Y1, Y2, etc. to define multiple targets. Some generic mathematics can be also used in this target definition. For example, you can use ID set over W, or you can use some simple expressions between different targets. And then the last one, we have checks. So here involves some MQA built-in functions, such as here we use a function named check22D. We will explain a little more about this function in next slide. Then we define different axes. X stands for L and Y stands for our target. So that means the plot I want to see will be ID set versus L. And then the P is W. That means the final plot I obtain will be ID set versus L versus W. If you notice that here is one keyword is check and another is compare. That means the same bias conditions or the same definition can be used in both check function for single model or comparison project to compare different models. That is very easy way to reuse the same rule file to different usage, to different applications. Of course, you can divide it into two different rule files and make it clearer. It's just per user's different preference. And then we will take a look at this check function. This check function, we name it check22D. We use this check function to let MQA analyze the trend, to check the trend of each curve in this plot. We use two flags here, times and increasing at first. We use these two flags to describe 4 different conditions. The flag parameter times is equals to 1. It stands for the curve is monotonic. Otherwise, it stands for it has 1 pink. And the other flag, 1 stands for increase, and -1 stands for decrease. So by the definition or different values for these two flags, we can clearly describe this full situation for the plot. The example we have here, if you still remember, is ID set versus L versus W. In this case, we define times equals 1 means it should be monotonic, -1 decreasing. So that means MQA will analyze this plot to see if the curve in this plot is monotonically decreased. If it's correct, MQA will report OK. Otherwise, it will report error. Trend is not right. So such kind of functions we have a full list, like check functions, check trend, check kinks, or check value, check crossover. We have all these check functions. Then sometimes we don't need to check, we just want to show some plot. Then we have a list of plot functions like save plot or compare plot or just to show the statisticals, etc. We have also calculation functions or complex number calculation functions for the RF applications, etc. Then besides this regular rule file, we have a special rule, we name it benchmark circuit. This benchmark circuit block can be implemented in rule file following by the regular rule we have just seen. As I mentioned, MQA will automatically generate the netlist and send to simulator to run. However, if we add this benchmark circuit into the rule file, MQA will use the user-defined circuit to run all the simulation. So this circuit can be defined by user. In this case, this example is 11-stage ring oscillator. What's the differences between this benchmark rule file and a regular netlist? You will find out we use some marks, some symbol, add symbol here to replace the instant parameters like WL or replace model. That means when we sweep different WL, MQA will replace the sweep value into the circuit and generate different netlists. The same for models. MQA will use selected model in MQA to replace into the circuit. That means when you change a model, you don't need to rewrite your netlist. MQA will automatically replace the selected model to the circuit and run the same benchmark run the same netlist as a benchmark rule. Other than this replacement, all the other circuit definition will be sent directly to the simulator. So we can still use the built-in function to check the benchmark circuit result. For example, I can check the ring oscillator delay, time delay versus temperature. When the temperature increase, if the delay will increase, or with the power supply increase, the time delay will be decreased or not. So all this benchmark circuit can also use MQA default check functions. Then I show as well here some more MQA result examples. For example, this plot is NP correlation. X is a P channel and Y axis is N channel. So it's VTH value correlation from NP channel. The right point is statistical running result. And the blue rectangle is the regular corner. So we will check the overlay between Monte Carlo simulation together with traditional corners. And then, of course, we have mismatch simulation. We can see the different Monte Carlo simulation in terms of local variation. So we talked a lot about the rule file previously because the key of MQA is the rule-driven QA process. This rule-driven methodology provides us a high flexibility for user to customize. Firstly, we provide a default rule file for user as a reference and also the base to work on. Then user could design their own rules, implement their own test circuit. The rule file will record user's IP on verification flow and then reuse, accumulate in the future. We can see from the working flow of MQA, we start from the MQA default rule, run it, maybe remove the rules that doesn't fit your process, and modify per your own requirement. We may add some new customized rule file, and then build your own standard verification flow. Then by the time going, we could accumulate more experience and improve the coverage of our QA process. That is the key advantage of rule-driven QA process. Step by step, you could build a standardized QA process. This process is not only automated, but also very flexible to be modified at any time. So before we enter to the Q&A section, let me give a summary of MQA. As the first commercial SPICE model validation solution, MQA is a golden standard tool for SPICE model qualification assurance. It has very comprehensive checking routine built in, and it supports all mainstream models and simulators. MQA can compare the differences between model versions by simulators and the Foundry technologies. It has very powerful and flexible reporting functions, also very easy to share QA results. I think this is the reason why MQA is broadly adopted by over 100 customers around the world. It's a powerful, customizable platform allowing users to accumulate and record their own technology and knowledge. Also automate and standardize the whole QA process. Well, this is all I want to share with all the audience today, and thanks very much. I'll pass to Vincent to host the Q&A section.
Thank you very much, Cedric and Janice, for your presentation and live demo. As Janice mentioned, it is now time for the question and answer session. So you can send questions in writing now through the Q&A functionality of the WebEx meeting, and we'll do our best to answer your question during the remaining minutes of the session. But if we run out of time, our presenter will respond to the remaining question via email. While the answer to your question may be published for others to see, we'll keep your identity private. So we have on the line also Winters Wu, which is Device Modeling Engineering Manager, who has already started to answer some of the questions in the Q&A. So let me see which one is not yet answered. So I've seen that one question is about comparing two foundries. Cedric, can you answer that? When comparing two foundries, how does MQA handle different device names for the same component?
Sure, Vincent. So indeed, it's a manual process. Normally, when you have a name for a foundry for a specific MOSFET or a specific device, you select it as Janice showed in the UI. You select this one, and then for the other foundry, you select another name, and it will be compared between the two libraries. So you can basically compare pretty much everything with everything. Then it's up to you when you have two foundries to know what you really want to compare and what is comparable. So you just select the name on one on the list on the lib explorer. On the other Foundry, you select the other name, and then MQA will send the correct netlist and then compare the results of what has been selected.
Thank you, Cedric. Another question for you, maybe for you, Janice. Is it possible to define on netlist with specific measurements and use them to controls, like process control monitors, PCMs?
I think yes. As the benchmark rule I have presented, with the benchmark rule, you can create your own netlist, and MQA also supports measurements. So you can overlay the measurements together with the model simulation result and using your own netlist.
Thank you. Another one which is coming, is it possible to define any custom function to be used as comparison check, example, delay of a signal on a node? Maybe this one is also for you, Janice?
Yes, I think the sample I just show is a ring oscillator, and the target is time delay. So MQA has such capability. We call it benchmark, and the user defines their own circuit, defines their own target. So if you look into the rule file, you will see that the output target is also user defined.
Thank you, Janice. Another one, can MQA benefit from hardware acceleration? Maybe this one for you, Cedric?
Yes. So there are several ways to accelerate the qualification process. So the simulators by themselves, if they are multi-threaded, so we'll use the multi-threading of the simulators. We can also parallelize several rules at once on different CPUs, so it's also possible. And the last option is that if you have load sharing tools like LSF or Oracle now, Green Engine, it can interact with MQA to be parallelized. So there are several ways of speeding up the process.
Thank you, Cedric. One which has been already answered through the Q&A, but was to be answered is, what operating system does MQA software run in? Maybe yes, Cedric, for you.
So MQA is the GUI is based on Java, so it's running on both Windows and Linux. So you can start from either Windows and Linux, but of course, if your simulator is only on Linux, it will not run on the Windows platform. So then you can use also remote machines to send that from the Windows. But if you have Linux already for the simulators, it's better to run on Linux on the Linux version for that. But the MQA software by itself runs on both Windows and Linux.
Thank you, Cedric. Also some questions related to the device model supporting in MQA. One was about IDMs, and another one was about FinFET. Janice, do you want to answer these two questions?
Yes. FinFET, we can use the standard model, BCM, CMG, or AMG. I think it's already published, so we can use it in MQA. And another one, EHAM, yes, MQA do support it.
Okay, thank you, Janice. Another one, which facilities are available to automate the QA flow? Specifically, is there a way to create a QA plan and replay it entirely without user intervention?
So I'll take this one. So like speaking, yes, of course you can use the GUI, but the GUI is meant to create a project that is completely then playable with scripts, so on Windows batch files or on Linux shell that you can just play and without any intervention for that. So it's a pretty easy way that could be customized through shell. So the GUI is mainly done to create all the projects, but after that, most of our customers are using it through through C shells or through batch files.
Thanks, Eric. And maybe, yes, the last one for today, and all the other questions, as I said, will be answered directly for you for email. Last one, can you use MQA to check readability device model? Maybe, Janice, you can answer that?
I think yes. We did some projects on that, and it depends on what model you are using, but basically I think the answer is yes.
Okay, so thank you, Cedric, Janice, and thank you also, Winters, to answer all these questions. I would like to thank you also. Since this session was prepared with the help of the MQA. MQA is a high-tech forum to discuss the frontiers of electron device modeling with emphasis on simulation-aware models. MQA will host the next workshop in Munich on April 11th and 12th. Discussions are of course about compact models, but also about including physical, analytical, and numerical models to clearly identify areas where there needs further research. So if you register for the MQA, you'll have also the possibility to meet with our Agilent device modeling product expert during these 2 days. Cedric, I'd like to get some closing comment from you.
Okay. So as a takeaway slide, is a brief summary of what MQA can bring as a solution to define or extend, if you have already one in-house, qualification flow for both Foundries and EDA providers. So through a complete built-in series of tests, MQA allows an easy way to challenge your current Foundry or benchmark several Foundries if you want to second source, qualify your current simulators or a new one, and also get meaningful insights on model changes when you're upgrading to a new PDK to see what has really changed between the 2 releases. So as we mentioned earlier, MQA is only one of the tools of our device modeling portfolio, stemming from model characterization with ICCAP. We also have layout characterization with AMA, and even we're able to tweak or retarget Foundry models if you have specific constraints using our tool called MVP. So if you have questions about these tools, feel free to get in touch with us or your ESOF sales rep to have more info or on-site demonstrations. So I will now let Vincent conclude this webcast. I wish you a very nice day, and I hope to get in touch with you very soon.
Thank you for watching this Agilent Technologies webcast. For more recorded webcasts, subscribe to our Agilent TM webcast YouTube channel. Remember, all our webcasts are held live. Interact with our Agilent experts in the live Q&A sessions and gain access to Agilent materials. To view our upcoming live webcast and to sign up for free, go to our website, www.agilent.com/find/web_seminars.